Uh, Welcome all. Sorry for to make you wait. I hope I'm audible. Am I audible? Somebody can just unmute themselves. Yeah, audible, right?
Yes, yes.
Sorry for what do you say? Um, for making you guys wait. I was just reading up on few things, so I'm already recording. Let's get started with this. Okay. Just casually, does anyone know what this graph is? What is this? What is this? Well, let's just because I guess you guys have had classes on uh, pure this what is it? Pure fluids, right? Phase one phase saturation domain. Anyone would like to just talk? How was your experience in your week two? It's something that you found difficult. Any comments or questions from previous classes? Anything before properly getting started? No. All right. Uh, and feel free to always unmute yourself and yeah, compressibility factor, yes. Yeah, so it's written there. But do you know what is going on? What is principle? I think should be principle rather than sure. But it should be principle rather than principle. Mm, so yeah. So anyways, if always feel free to just interrupt me and ask whatever you would like. That is totally okay. That is what we are here for. This is the second interaction session. Any comments on the previous sessions or doubts from the recorded lectures are welcome. Please let me know. Okay. Yeah. So let's get started. Mm, this is my introduction. Just quickly, I'm Shri Sai Gupta. I'll be taking your live interaction sessions. I will be the teaching assistant for this course. This is my mail ID. I'll update this website link, but this LinkedIn link is okay. So if you want to reach me out, that you can do. Um, I also realized that there are people from also non-mechanical background. So maybe it is better to continue doing some selected problems, no matter how simple they are, so that everyone is on the same page. About this graph, let's come to this graph a little later towards let's say in the next class or towards the end of this class. But something which I wanted to quickly discuss is the loose ends that I left in the previous class, right? Previously, we kind of started writing something mathematically to define a state. We stopped, and the reason for me to stop there was that I was not being mathematically precise, and I was not able to be mathematically precise to define a state. And that is essentially because we need to realize, as I think Akash, correct me if I'm wrong, I think Akash mentioned that properties are exact differential. Now, that is not a very good way of, um well, this is a precise way of defining properties, or let's say state properties. State properties. There are a lot of things that we call this as state properties, state functions, point functions, and so on. So I'll just let me tell you that although this is a very precise statement, one is it is not a statement, it is not a definition, it's a statement. Secondly, the statement relies on heavily on the fact that there has to be a differential quantity in place to first define state properties. And so it's not self-containing. You don't, it does not make sense independently. You have to set a context to it, right? It's not self containing. And to make it self-containing or to provide the context behind this, we essentially have to draw a 2D graph. Uh, that is what we typically do. Everyone just quickly refers to a graph, says that there are two states, and you're moving between these two states. So while moving between these two states, you essentially pick a small length over this trajectory. Say if this quantity changes, there will be a differential. And if this differential is an exact differential, it's a state property or point function or state function. But again, one thing is that there are a lot of uh, givens that you will have to rely on to define this context for state functions. See, am I making sense? Am I being very precise, or am I being too detailed about this thing? Uh, but let's quickly do this. It will not take too much time. Even if I'm taking some time on this integrities of this definition, let's be precise just for the sake of completeness. As I was saying, you have to first rely on paths. So in some sense, you have to get into the definitions of path functions, because even when we talk about exact differentials, uh, have you come across any inexact differentials in before in your life, uh, ever before, before getting into these definitions, right? And someone mentioned that if I write x dy, this is a inexact differential, and generally we will define it as a different, what do you say, let's say di, where let's say if I have a ei integral a line integral, and I write it like this. So what I say is that di is x dy, right? And so we see that this integral over a path, is over a line. And so to even define this integral, you need to define a path, which is c. Let's say this is the curve c. So that is what I wanted to just first quickly say, that in all, you need a lot of things to define a state functions. First of all, to first separate state functions from path functions, you need to define a path. Secondly, you are also relying on a state space. So you are kind of saying that there exists a primitive state space, right? There exists some states, what do you say, that you are already aware of, right? So in definition, while defining a state function, you are already saying that there are some primitive states. So now I'll come to the point. What states are we well aware of? So first of all, we have to accept the fact that state functions definition will not come out of thin air. You have to know some primitive state variables. Okay, so now I want you guys to maybe type in the chat or unmute yourself and tell me some primitive state variables that you're well aware of, which you know that are states. You get my point, right? What I'm trying to ask. So this S1 and S2 is something that we will know before knowing that there are other state functions as well. So we know that there are some states. So essentially what I'm trying to say is that for any system, see, state is essentially saying that a system is under some condition, and you pinpoint those conditions. Combinations of those conditions become a state. The state space is a point. A state is a point in this state space, and state space is a collection of all possible states. So let me make it more simple. Let's say volume V, which is, we know this is a state, isn't it? And we also know, let's say, what else is a state? Pressure is also a state, right? It's Pascal. This is also a state. Why are these two states? Can you tell me this? Anyone, please try to interact so that, or even if I'm not making sense, inform me so that it's for the say like it's for the advantage of everyone. Uh, Try to interact. Tell me why these two are primitive state functions do we know of? Like we know of. Let me be let me state something else also as the state of the system. State of the system, you know, right? In colloquial language, we know what state means. System, what conditions is the system in, right? There are some states that we know of. The volume of the system is a state. There is a state is let's say pressure. Pressure is something that you will need to define. So I'll come to pressure, but there is also something called as velocity is also a state, right? Uh, Position is also a state. The system, the position of the system is also a state. Um, the angular momentum of the system is also a state. So L. Acceleration of the system is also state. V dot. I'll put it as V dot. These are all states. And why are we calling these states? See, primitively, I'll tell you what. Primitively, when people were looking at thermodynamics, they were looking at uh, macroscopic measurements. Okay, this is what I was reading before joining the class. This is like the chapter one on a classic book on thermodynamics, and I was reading this book, and it says very well in the starting. What part should I read? That thermodynamics is all about macroscopic properties. Okay, so this is the essential message of this whole discussion which was going on. I also quickly referred to this book in my last session also, right? But I didn't do justice to this discussion then because I had not referred to it beforehand, but I was just reading about it now. So as I was saying, uh, so essentially, primitively, when people were looking at thermodynamics, they were measuring macroscopic properties. And the idea there is why do you look at and why do you start defining states is that these are properties that can quickly define states, right? I'll tell you why. Suppose if I go into a very atomic picture, microscopic picture of a state, right? Suppose I have a glass of water in my study. I'm studying a glass of water. Do you know what all things will I measure? What all things can you measure? Let's say states are measurable quantities. What are these measurable quantities? Now, at least now I have made this very precise, like very simple, right? What all things can you measure? Let's say I have water, or let's say I have a glass of some substance. I don't know what that substance is. What is the what properties can we measure? So we can measure, let's say, because I've said it's a glass, do we know where it is stated? Like where is it kept? So position, is it moving with some velocity? Is it revolving around with a velocity? If it is an object, all these quantities will come in, right? Mechanics of it. Acceleration is an important thing. How much volume of water do you already do you have? Right? How much volume of water do you have? Uh, Pressure is something that will come in with thermodynamics. Let's leave that part. Uh, what else? Yeah. So composition. What is the composition of the system? Right. This is also something we call it as phi. Velocity. This is what is it called? It is called potential. Which potential? Chemical potential. So chemical composition of the system is also there. Uh, Right. What else? Now I'll tell you. So essentially, this discussion which I was like I just quickly was reading through it says that there are a lot more state variables that um, that can describe a system. See, we all these measurements which I have done are macroscopic in nature. If I start going into the microscopics of the nature, then I'll measure the number of atoms in this or number of molecules in this substance. For every molecule, I will measure this position, the velocity, its angular momentum or angular velocity, let's say omega, acceleration, so v dot. So so I'm going too deep into this, but let's just bear with me for some more time. So so this all these, and there will be for every one of them. So let me point that out. So every one of them will have a velocity, and so one thing which you'll note is that there are innumerable. Let's not say innumerable, but let's say uncountably, countably many number of states. If we were to go to depths to define a system, right? The forces between them, or I don't know. It force from the forces comes pressure. So I'll let you know about that soon. So you see that on a microscopic, if you go into the microscopic scales, uh, you essentially have a lot of states. Okay, but in thermodynamics, we essentially are saying when you are into this macroscopic scale, one thing is continuum hypothesis come in into the picture. So I'll bring continuum hypothesis in a while, just into the context in a while. But let's quickly understand that once we are in a macroscopic scale, a very less number of so from a very large number of state variables or state variables that define the state, we can quickly reduce them to some small number of whatever state variables or variables that define the state if we look into the macroscopics of it, right? So one thing is that just read this line. The most striking feature of macroscopic matter is the incredible simplicity with which it can be characterized. I'll tell you why, but what do I mean by it? See, essentially, so I'll give you an example. Essentially, so let's say these are the these let's say states. This is something which I'm not concerned with. Let's talk about the four velocities that we will have, right? And some forces. Let's also keep these so these five quantities. Do you realize what this essentially gives us? Essentially, if we integrate over all, if we sum up over all element, all molecules, and add all kinds of velocities, right? Essentially, you're going to get energy. That is what we are going to get. And an energy is a single variable. So if we integrate over few things, if we can integrate over space, or let's say over number of elements, number of atoms, we get some value. See, you realize one more thing that, as I mentioned, velocity is a function of position, right? Uh, every element will be at some position. So if I traverse in the space, I will find velocities in different space positions, and it will also be functions of time. Okay. Similarly, so all these properties will have dependence on the position and the time. So time will not be ti, time will be t. But suppose I integrate over all this, as I was saying, sum of all energy in the system, add everything. What do you think? Will it be a function of space? First of all, I've integrated space out. That is one thing. And I've taken an average. So the E, let's say I'm kind of defining something, some quantity as some over I, and I'm multiplying VI square. Let's keep it that simple, right? And then I'm dividing it by NI, right? What do you think? Does E will depend any more on T, time? What do you think? It will depend on T, but it will be something like this, let's say. So some quantity E naught, which is not no more a function of time, plus some delta E, which will be dependent on T, but delta E will be much smaller than E naught. And for the sake of simplicity, we can essentially say that E will be just E naught. So in some, so you realize that when you integrate over things, or if when you're looking at macroscopic pictures, you're kind of sim the simplification that you get, first of all, in the number of state variables is very high. Those variables are not depending on space and they are not depending on time. So essentially, those primitive variables which I was talking about have to be these macroscopic measurements. Okay. When I come into thermodynamics or thermals of the system, so these all quantities are indeed important, and they go into the mechanical state of the system. So when you are writing the spring mass equation, position, velocity, and acceleration are definitely states of the system, right? But for a thermal system, let's say there is no mechanics going on there. It's all in thermodynamically, or let the system is at state overall. So all atoms, and you multiply so you take a vector sum of all velocities, and you'll see that the average velocity, uh, V average, will be something V t, which will be a function of time, uh, and this V will be much smaller than 1. Let's say 10 to the power minus 15 meter per second or something. So in this case, we can essentially consider the velocity of the state to be at rest, right? That is what we say when we're considering a system at rest. That is essentially what we are saying. We are not saying that the atoms inside it are not moving. They are moving, but the overall effect of this is not letting the system to move its position or something. So let's say these four quantities are now no more into the picture, and we are into the purely thermodynamic regime. Then what all quantities do we measure? And let's say this is also a pure system. Let's say this is a pure system, so that we can simplify and we can now start concentrating on. So now we go closer to the definition of state function. Now we start making things precise. So one thing that which we know is that the system's density, or let's say mass, is also a state, right? Mass of the system, and because velocity is also a system, let's say P and density, pressure and density. So what is P? P is essentially the force that it will be applying on the wall. So the beaker I was mentioning, there is a glass of some substance. What is the force per unit area that you are applying on the system, right? So that becomes the pressure. Okay. So now these two quantities are at least two primitive variables that we know of, two primitive state functions that we know of, right? There is indeed one more state functions, generally for a pure substance. For a pure system, for a pure system, there is another state function. What is it? So Jyotirmay is typing. I'll just quick wait for him to complete so that I can read his comment. Quickly do it. Okay, so anyways, let him type. Yeah, so as I was saying, there is another state variable that we know it's very well known, and that is temperature. Right, as he mentioned, temperature. Now my question is, P is measurable, right? P you can measure unit using a manometer. Density is measurable because you have a scale, you can measure the volume, and you can, or let's say you have some calibration kind of stuff so that you can measure. So density is also a macroscopically measurable quantity. What about temperature? Is temperature a macroscopically measurable quantity? If yes, please let me know how. You can unmute yourself, Jyotirmay, if you would like to answer. Okay. So one thing is that temperature in temperature R is measurable using temperature scale. So we have thermometers for that. But in principle, temperature, defining temperature as a state was uh, zeroth law of thermodynamics was all about. So you see, in principle, temperature is not mathematically, or it's not a macroscopically well defined quantity. You can't see temperature, right? You can't measure temperature directly. You measure it indirectly. What you do is you define that there is some water which is at 4 degrees Celsius. You know that this water is at 4 degrees Celsius. You have a mercury in a column. You see that when this mercury is in thermal contact or in contact with this water, it is at some length. And if you, and then again you have another substance which again you define that it is at some temperature, let's say 100 degrees Celsius. Let's say 0 and 100 degrees Celsius, the boiling temperature and the melting boiling and melting temperatures of water. And that is how you define the Kelvin, the Celsius scale, right? So those two quantities are, so you see that there is you don't directly measure temperature, and that is what zeroth law was all about. Zeroth law actually stated that temperature is a state in itself. Temperature is a state function. So that is what it is about. So that is what I was trying to also kind of hint in the first thing, that temperature is another state variable. So that is what I was just quickly I wanted to discuss this. And now once you have temperature in your understanding and you have a 3D or 2D space, a state space, then you can talk about some integrals or something. Then you can talk about x dy or y dx to first say that these quantities are not well defined as a state themselves. You need, like, any function of x and y will be a state, but some quantities like x, t, y are not state functions. And if I were to quickly, what do you say? How do I show this to you? Q is, can I do that? Let me think. Right. So now path functions get well defined. I'll tell you how. So now once you know in this state space, you can measure few quantities. Let's say you measure some quantity, and that quantity uh, is not a function, or it's not well defined in this space, gets to be a path function, right? And that is the most known, or the most well known of these two are q and work. So the work and heat are the path functions that we generally distinguish state functions from, right? And how do you define q? So generally you write something as di is x, let's say x dy plus y dx, let's say, right? But in thermodynamic sense, we write it as del q. So it's not dq, note that, we write dq. So to specify that this is not an exact differential, or this is, see, this is also not an exact differential, but generally you don't write it this way. You generally write del q, but del q also, this notation is very unique to thermodynamics, but it is still the same as this. That is what I'm trying to just get at. Okay. So this is something which I just quickly wanted to uh, discuss, because this is something which I did not properly do it in the last time. Okay. So this is one thing. What else was I trying to say about this? Yeah, so del Q gets defined as the heat transfer, right? How do you write it? You don't have an expression for it in terms of P or T or V, right? Because this it's a path function kind of thing. You need to know uh, the path that is that you're traversing on to actually write this. dq is something, right? So can we write it as mcp dt This is a particular path. Mind that this is not a universal equation. This is not an identity. It is in a uh, what do you say? Or let me write it as dh. This is again in a particular condition. This is not or particular path. This is not an identity. You can't write anything about del q equals to. You can't write anything or del w. So del w you can actually write. Let me write that. You write it as pdv, right? But sometimes you also write it as vdp, right? So how do you? This is also not a universal thing. That is what I'm trying to say. This is not a universal thing. Just remember that. Okay. Indeed, let me just quickly, because in the interest of people who are already aware, or maybe this is the first course in thermodynamics, so I should not discuss it here, but let me quickly just do it for people who are already advanced in it. You know about this identity, right? We'll discuss this later on. Just TDS, uh, what is it? PDV, right? Is this correct? No, no, no. This is not correct. This is correct. I think this is correct. So, and we also know that du, which is U is the internal energy. I've not still defined internal, what is internal energy, first of all. I've even not defined energy, or maybe professor has defined it, but anyways, du is also del Q plus delta W. Uh, okay, so this has to be small value, small. Even here, if I write okay. So even here, so maybe the thing I was trying to point out is that this is something which is not universal. Okay, you can't write anything. What is del W? Okay, so just note that. PD actually should be. So this is what I'm trying to say. This is a state equation. This always holds. This is an identity, but this is also an identity, but you can't actually express del Q and del W to be some expression, okay, in TDS or anything. Because if you do, then essentially what you're trying to say is that heat transfer or work is also a state function. You can't write them. For only a particular process, you will be able to write it. Once you specify the process, then you can say that di is xty under the constraint that we are moving along that some dx. So C will be defined by say, so C will be defined as like what? Dx by dy is, let's say, some quantity, right? Some C, and x will be some value, right? Some m. So in only under this condition, di gets defined. Then you can actually say that dx is dy is dx by dx by m. So you now see that this becomes a function of state, but only under particular path. Okay, so that is one important thing. Anyways, so this is something which I just had to introduce because I had kind of opened it in the last time. Let me go back to again solving problems. I think that is the best for our lectures. Okay. Yeah, so this is one thing I wanted to quickly discuss. I'll remove this part and I'll open the. So give me 2 3 minutes so that I. So let me open Google here. Yeah. Let's do the questions for the week 2. Okay. Hmm. I'm trying to just quickly access that those questions. So just give me a couple of minutes, okay? We'll go to week two, okay? Let's see what week two has for us. Right. So microscopic. So we have certain number of quick MCQs. So let's just quickly discuss those. What is this question? Let's see. So the first question is, so now it's better for me not to explain these questions and you to just answer them if you know it or attempt this. Because if I just go ahead, this is just a simple thing, right? Meanwhile, I'll also paste other questions. Okay, so maybe I'll pick Pradeep. You have been Pradeen. Sorry. Pradeen, can you please unmute yourself? We have been trying to get in, and then I think your net is not that great. Would you like to attempt these two quick MCQs? No. Maybe anyone else? Rabin, Jyotirmay. I can just quickly give away the answer. Uh, the first one is, what is it? Use a pen here. So microscopic properties are obviously associated with molecular structure. Energy possessed by it is not related to microscopic properties. So these two comes into the mind. But again, independent of outside frame essentially means what I was saying, that if you average things out, the overall velocity of the system or overall momentum of the system gets added to the all the molecules of the system, right? That is something which should not depend on microscopic properties, right? Microscopic properties, like what all microscopic properties can we think of? Yeah, so let's say VRMS. The root mean square of velocity of all all molecules, or Vmax and all these things. So maybe I can talk about the kinetic energy, kinetic theory of ideal gases. But again, let's not do that. I think this is fine. So we know the answer to be this one. Now, this is an interesting question. I kind of answered it in the very starting. Uh, Internal kinetic energy. What do you think? Enthalpy, entropy, temperature, heat. So first of all, which of the following properties eliminates heat? Entropy is something that has not been introduced to you very well. You know something about randomness and entropy, but anyways, summation of internal kinetic energy is associated with temperature. That is the simple answer. And that is why I was trying to say that temperature is something which is not a state in itself. It is a manifestation of internal kinetic energy. It kind of comes in from there, right? Uh, and it's kinetic energy. That is also important. It's not total energy, right? So if it was a total energy thing, then maybe internal energy could have also could have also come in the picture. And in general, U or internal energy is a function of temperature and pressure both. However, kinetic energy is only a function is only a function of what do you say? Internal kinetic energy is a summation of V, so summation over VI square, right? This is essentially dependent on only temperature. That is what temperature is kind of like that is what temperature denotes or is about. Okay, so that is how the temperature is defined, to be honest. Okay, Okay, that is one thing. So you know, if the temperature is higher, you expect the atoms to be moving more rigorously and so on, right? That is one thing. Anyways, let's go to the other questions we have. I'll remove these two questions. Now the third question is again similar. Work and heat are properties of the system. You already know the answer. No, these are not properties of the system. Characterize the macroscopic. So I've skipped question number 3 because it was very rudimentary. What about fourth? Let me paste 5 also. Paste a couple more of questions. Okay, so let's attempt these 3 questions. Characterize the macroscopic and microscopic kinetic energy from the options given below. Macroscopic properties, as you know, is organized, and microscopic properties are disorganized. That is how they're defined. That is one thing. I think this is the correct answer. Then in an adiabatic process, what is an adiabatic process? Del Q is 0. Okay. So already now we have defined path. Okay. Note that. In an adiabatic process, you have kind of defined a path. Okay. Have you, let me correct myself. Have you defined a path yet in an adiabatic process? Well, you haven't. I think you have. Reversibly, you have defined a path. Reversibly, you have. Okay. From second law, you kind of have defined a path. So yeah, you have defined a path. The net heat transfer between system and surrounding is. See, also another important thing is the notion of path kind of requires you to talk about quasi-steady processes. Okay, there are also processes where the thermodynamics, all your rules will fail. Okay, you can't they don't fail, but you can't do all these things. Okay, you can't even write this. They are such a fast, they are such fast processes that you can't write few things. So again, that is again, but still paths are not defined. So even paths require you to have a quasi-steady picture. Okay, so paths are not defined because again, quasi-steady means that there's a small change. Okay, that is important. So small changes have to be there. So for you to define paths, okay, they cannot be very large changes. Okay, something, let's say, so those so generally paths are defined by a solid line. But when you have some large changes, immediately large changes, so that you define with the arrow, or sorry, with the dashed line. So let me quickly incorporate that here also in our picture of our discussion. Outline I changed to full line. Okay, not this. Is wrong. Hmm. Okay, so this is one thing. Anyways, coming back to what we were saying. Uh, So in an adiabatic process, net heat transfer between the system and the surrounding is 0, already defined. So these are quite very, so even before going to the options, I kind of discussed the answer. So they're that straightforward. Which of the following type of work is not a non-mechanical form of work? Okay. Work done in a reversible cell, dielectric solid, work done due to magnetization, and shaft work. So shaft work we know is a mechanical form of work. Again, this is theory, okay? We just know it. We read it and we kind of just read it out, okay? Or we just kind of dump it out there. Nothing new. So we know shaft work is a mechanical form of work. What about magnetization? Magnetization is also a mechanical work, okay? because you have force, magnetic force, and the work will be magnetic force into velocity. I think so. Yeah. Then dielectric also is a mechanical work, I think. Yeah. And what is a reversible cell? I think what they mean is, we say, what this. Great. Anyways, as I was saying, got intrigued by this already, these shapes getting organized of themselves. Anyways, I think this should be the answer, but let's quickly check using the book, okay? Not sure. Okay, so it says not a non-mechanical form of work. So this is electrical work, this is magnetic work, this is a mechanical work. So not a non-mechanical. So it's basically saying what is the mechanical form of work. So let's quickly review this because I kind of got it wrong. Quickly we will review it, okay? Should be, this book should be where? Try this. Yeah, I kind of have to. So mechanical form of work is only. So let's see what mechanical form of work is. Okay. So this is Sengel and Gazar, mechanical forms of work. Okay. So let's just. This is just a what do you say? Categorization. So shaft work is one of the mechanical form of work. Spring work is a form of mechanical work. Work done on elastic solid bars is a mechanical form of work. Stretching of a liquid flame, raising and accelerating a body's mechanical work. Now let's look at non-mechanical form of work. Oh, wait, so mechanical, some examples of non-mechanical work are electrical work, magnetic work. There is also electrical polarization work. So these three are the non-mechanical form of works. Okay, you just have to kind of memorize them. Okay. Anyways, so let's look at the other questions quickly. This is something which I didn't want to do initially. It was kind of rudimentary, but anyways, let's get to a good question now. So, simple question, not a tough one, but let's see. Okay. So electrical power is generated. Let's read this question. Electrical power is generated by installing a hydraulic turbine. Maybe you won't be able to see it that clearly. Let me zoom it a little bit. So electric power is generated by installing a hydraulic turbine generator at a height of 100 meters below the free surface of a large water reservoir that can supply water at this flow rate steadily. If the mechanical power output of the turbine is 100 kilowatts, electrical power generation is 970 kilowatts. Determine the losses in the turbine unit and overall loss. And the overall loss. Okay, fine. So what is going on? You know, this is one. Okay, this is two. These are the water levels. Let me mark the water levels for you for clarity. This is again water level one, and the difference between these two water levels are due to gravity. The work will be essentially due to gravity. How do I know that? Because this is P naught. This will also be P naught, right? So whatever work you're going to do will be rho GH. This is the pressure difference between 1 and 2. Okay. 1 and 2 will be uh, rho GH. Now, any pocket of the fluid which flows from here to here, let's say it has a mass of rho and it will have some volume V. So the potential energy, decrease in its potential energy will be just rho GH. Okay. So from there also we can see this pressure differential is not essentially important. So this is like force. and this is the energy version of the same thing. Okay. So this V is coming. So if you do energy per unit volume, you'll get rho gh, and pressure has the units of energy per unit volume. Okay. So fine. Now what is it trying to say? The H is 100 meters. G we know. Now rho. So this is giving you a mass flow rate. Okay. M dot, right? You have a mass flow rate. So now it will give, so mgh, m dot gh will give you what? It will give you the power, right? The power that is, so if you have a steady flow, essentially per unit time, this much amount of mass is coming down, right? So it's basically mgh per unit time. So from there, we kind of say that this is power, right? So this is power, or let's say W, or no, let's say power only because W is work. Or I could use W dot to signify that it is power. Uh, so if the mechanical power output of the turbine, so basically now what happens, turbine, so this, let me draw this part, okay? Let me quickly explain it to you how this energy flows, okay? What is happening with the energy. So you will have a fluid, okay? You have fluid, okay? Or, or let's not say fluid, let's say stream, fluid stream. So you have a container stream that is losing some energy while coming down. So comes down, loses some energy, turbine picks it up and gives it to the generator. It gives you to the it gives it to the shaft, by the way. From the shaft, turbine picks up, and there are two places of losses that so losses essentially occur in the turbine end, and this is generator, okay? I'm writing it incorrectly. So generator. So these are the two places where the losses will happen. Okay, so there will be leakages of power in these two places. So first of all, let's calculate what this power is. So this is 1500 into G, which is 10, into H is again 100. Uh, right, H is 100, right? So this is 10 to the power 5, 1.5 megawatt is the power of the or energy available, right? 1.5 megawatt energy is available. Turbine is producing, so this power or this power, which will be equal. So shaft, both sides of the shaft is rotating at some speed. There will be force. Let's say there is no, so torque will be transmitted by the shaft. So essentially the same torque will be transmitted by the shaft. So the shaft power will be what? Is 10, it's 1 megawatt, as it says here. And then generator is also producing some power, which is 9.7 megawatts. Oh, sorry, 0.97 megawatts. Okay. So now we are just told to calculate the losses in the turbine unit. So the losses in turbine unit is 500 kilowatts. And then this one is 30 kilowatts, right? So let's check what options are there. Let me check the options. So the options we have is 500, and so this one uses 9.8. So that is why it is kind of giving options like 502 kilowatts. So the options are, I'll also put up the options for you guys to select from. Okay, so now I think you have options on your screen. Let me remove all this. Let me, yeah, so the option you have is from the turbine unit and then overall loss. Overall loss should add up, right? Should add these two, so 30 and 500. So I think if it is 9.8, so then you will get 472 and then 30 gets to be 502. Okay. This should be the options. B. Let me check. Yeah, 472 and 502. So this is fine. Let's move to something else. Some other question. Okay. So consider, okay, I'll just paste the question up in the screen for everyone to be able to see. Consider a fan located in a 2 by 2 meter square duct. Fan motor consumes this much of watt of electric power that then determine the minimum air velocity near the fan. Consider the air density to be 1.2. This is the density. So basically, what is it saying? You have been given rho, you have been given an area, you have been given power, and you have been asked to calculate minimum air velocity. Okay. Uh, Now we'll have to see why is it written minimum? Why is it not written as simply air velocity? Okay, let's talk about that. So again, similar thing. You know that there is power is kinetic energy. So you have m v square by 2. But now power has to have a flow rate. So this will be m dot v square by 2. M dot will be rho v uh, a, right? And then you have v square already with you. And this is 2. So you have rho a velocity. Let me write v as capital V cube by 2. This should be the power. We know the RHS. Yeah, we know the LHS. We know density. We know area. Let's go ahead and calculate velocity. So this should be 1.2. So basically, you divide 400 watts, divide by 1.2, you multiply 2 here, and area is 4, right? So this gets cancelled to be 100. This is 1000. This is 6. And then you have a cube. This will be 10 by 6 to the power 6 cube root. Okay. Cube root of 6. Let me just quickly calculate what is cube root of 6 using my calculator. 6 to the power of 0.33 minus 0.33. Yeah. Okay. Comes out to be 5.5 something meter per second. So the options you have is 10 meter per second, 4 meter per second, 5 meter per second, and 8 meter per second. Definitely, you can't have these two, and you cannot also, you might have 4 at some boundary condition, like at low velocity locations or something, but because the answer is 5.5 and the closest value is 5, we'll select 5 and the correct answer is also 5. So I don't know why minimum was there. Didn't make much sense. Maybe to just remove other options, but then 4 is also there. Okay. So does not really make too much sense, to be honest. But anyways, this was again very simple numerical questions that we are doing. You have to look up other questions. These questions that NPTEL people have provided are not very good. Have to at some point have to do some good questions. In the first few weeks, it is okay because nothing very technically precise is being taught right now. But anyways, you can't just simply discredit what is being taught, what is being taught. So yeah, should not discredit it. Okay, so now let's do this ninth question. Yeah, we just have two more questions with us. The next question is, a man weighing 75 kg is pushing a cart with its content that weighs two-thirds of his weight up a ramp that is inclined at some angle theta naught from the horizontal. If the work needed to move along this ramp at a distance of 50 meters is 500 kilojoules. Consider the man as the system, then determine the angle theta. Okay, again, if I draw a free body diagram, there is some wedge. This is theta. This guy is carrying also some weight. So his own weight is, so he's pushing a cart also. Okay, he's pushing a cart. So there is a force on him along with his weight. Okay, so this one is 75 kgs, 75 Gs. This is two-thirds, so this is 50 kgs. So that thing is itself 50, whatever, 50 kgs. Okay, whatever he has, the cart. Okay, 50 Gs. Okay, 50 Gs. And it's a some small angle. That is very important. Okay, why? I'll tell you why some small angle, because essentially what they are going to say is sine theta naught is roughly equal to theta naught. And so is this true for tan theta naught. Okay. Because of this identity, I think they're kind of using it. So okay. So that is why this will be 75 g theta naught plus 50 g theta naught. So you get 125 g theta naught. And this is the force this guy has applied. Force into distance is work, which is 50 meters. And this is along this ramp. So that is why I'm able to just quickly multiply it, okay, into 50. Otherwise, I will have to take a dot product. Okay. If it was a height of 50 or something, then I would have to take a dot product. But because it is saying along this ramp, so I know this direction of this 50 meters is in this direction. So the force is kind of 180 degrees with the distance. And so the work is should be minus, right? There should be a minus. And so this 500 kgs is not work done produced or work produced, it is work supplied. So 500 kgs is also minus 500 kilojoules, and this is 10 to the power 3 because of kilojoules. So this minus gets cancelled. This is 10 to the power 4. G is 10, so I cancel this with 10. And theta is 10 to the power 3 by 125. I think this is 8. It should be 8. The options, I'll show you the options. Please correct me if I've made some mistake or something. Just quickly tell me. See, look at the options. It is quite bewildering. Why are the options so weird? Yeah, you have the options, right? You have the option. 150, 50, 120, 90. None of them are small angles, yeah. inclined at some small angle of theta naught from the horizontal. From the horizontal, yeah. From the horizontal is theta naught. What are these options? But from our calculations, we are getting 8. So let's leave it there. Sometimes their options are also weird. Hmm. Let me put this up in ChatGPT and see if kind of I get the same thing. Okay. Okay. Pull up ChatGPT for you guys. At least this is a quick sanity check. If I made some stupid mistake, ChatGPT will be able to catch it. Come on, answer, man. Come on. Mm-hmm. I was just taking so much time. Seems like a very tough question, huh? Interesting. Let me put it up to Gemini or something. So I'll close this bar. Pretty sure this is because of internet connectivity. Question is not that tough, to be honest. I don't know. But none of the options are compatible with the statement of the question or the problem, to be honest. Okay. So meanwhile, let's see. They're not answering. Huh. It's answers. So theta is 8.61. So they use sine theta. It's fine by me. So we're kind of getting the same thing. Sine theta was 8 point something. I got, instead of saying sine theta, I said theta. So ChatGPT kind of agrees with my answer. Sine theta is 8.16. This is physically impossible for sine theta to be less than 1. Okay. Right, I didn't realize that. So theta is not in radians, okay? Theta is not in radians. That is important. I was talking about 8 degrees. This cannot be 8 degrees also. This is question is the issue. With these values, 500 kilojoules is far too large for lifting a 125 kg system over 50 meters. The data is inconsistent. Likely intended value is 0.0816. So if it's 500 joules, let's say, then also this, so then let me, if it were 0.0816 sine 0.816. Okay, let me check what is sine inverse of 0.816. It should be 0.816. Okay, 0.0816 into 180 divided by pi is how much? 4.7 degrees. Probably this is the answer, okay? Probably. If it's 5 kilojoules, then that works. But otherwise, sine theta is 8.16, which is impossible, okay? So this question is kind of wrong. Okay, that is one thing. Right. Let's look at the other questions. Go for the next question. An oil pump is just drawing 35 kilowatts of electric power while pumping oil with this density volumetric rate of zero point 0.1 meter cube per second. The inlet and outlet diameter of the pipe of the pump are these. The pressure rise of oil is the pump is this much. Motor efficiency is this much. Determine the mechanical efficiency of the pump unit and the overall efficiency of the pump motor assembly. Fine. Simpler question. Like it's not very different from the other questions we have been doing. Let's just quickly do that. We're pumping 400 kilowatts of 400 kilopascals of power, as I told you, delta P into specific volume or volumetric flow rate, right? So V dot is power. You can check it. Units wise, this is power. So 400 kilopascals of, so we know W is PdV, right? PdV, or let's say VdP. You integrate it. So this actually requires you to use this formula, by the way. Work done is then V delta P, and this is work done. So if you want to calculate power, you do this. So this now becomes zero point 0.1 into 400 kilopascal, so 10 to the power 3. Now what? Uh, One work done, pressures are this much. Um, what is this? Now, if the pressure rise of oil, motor efficiency is given to be 92%. We have been told that this is 35 kilowatts. So the total, what is this much? Let's calculate this. This one gets cancelled by 10 to the power 2. So this is 4 into 10 to the power 4, which is 40 kilowatts. Now I know that because this sum says as 35 kilowatts, so then overall power, overall efficiency should be 35 by 40, which is like 7 by 8. 7 by 8 is how much? So you do 0.8. So you multiply 0.8, 70 by 64, 687, something 87. So overall efficiency should be around 87. And determine the mechanical efficiency. So what, okay, so now what will be the formula to find mechanical efficiency? So overall efficiency, see, as I mentioned in the previous diagram, right, where turbine and generator was, there is some power that motor gives to compress the pump, and the pump supplies it to. It is wrong. Wait, how come we are providing more power and consuming less? That should not be possible. Wait. I did it wrong. What is this? We are kind of, so 400 kilopascals and this thing. Okay, let me check again. Chat GPT. Let's see what Chat GPT says. So we also multiply the kinetic energies also. Yeah, interval. Wait, kinetic energies we'll find out. Yes, yes. So we'll also have to sum up kinetic energies that we have to do. But just not this. Kinetic energies also will have to be included. We can't just ignore kinetic energy. That is why these areas are given. That is important. That is what. Even then, okay, okay. So essentially, that is the interesting part. Let's do this. Okay. So now areas are given to us, right? See, we also need to calculate kinetic energy difference. Initially, so what is kinetic energy? Let me write it as what is delta KE. Okay, what is that? It is, as I told you, m dot into v square by 2. Okay. So now m dot is something that I know by saying that rho q and then delta v of square, the delta of v square by 2. So this should be, uh, okay, one more thing is we know q is uh, v into a, right? So from that we will calculate delta v should be delta v square. Where should be what? This should be delta. You can take q square out. This will be 1 by area square, right? So if I do outlet minus inlet, see how outlet has a higher area and inlet has a smaller area, and this quantity will become negative. So essentially, this will be 0.1 square times you will get 1 by 0.12 square, right? So 0.0144 minus 1 divided by 0.0064, right? Now, this is how much? So I'll take one more thing as common. I'll take this 10 to the power 4 common, okay? So that you have this much there times 10 to the power 4. So this becomes 10 to the power square by removing this part. Now this you take either common or whatever. Let's take, because this is 8, right? So let's take 4 square common. You can take 4 square common, right? 16 4s is 64, right? And this is 12 into 12. So 12 into 3 is 36, right? We can also take another 4 common here. This becomes 16. Can we take, yeah, yeah. So this becomes 9. This one is 1. This is 8 minus 8 by 9. This is minus 8 by 9, which cancels out to be 1 by 18. Okay, this much. Now this is delta V square. Okay. Now I also need to multiply it. So delta KE is rho is 900, and what is Q is 0.1, again 0.1. So 90 into, then minus there. This is 100 divided by 18. And now I know that there is a cancellation that will happen. So this will be 100, 500 minus 500. This is 5 minus 500. Wait, what is it? Should it minus 500? Wait, what is it? And then you also take a half. See what I have done mistake is, so rho was 90, Q was point 1, so 90, this is 90. And then this is times minus 100 divided by 18. What I didn't consider is divided by 2. Okay, that is important. Didn't consider this. Now, this is 1, this is 5, minus 250 it will be. This will be minus 250. 250, what? 250 units. Let me do it again properly. Hmm. Delta Q. Delta kinetic energy. How much? It's basically you have to first multiply m dot, which is rho, which is 900 into velocities. So this volume of the flow rate is times zero point 0.1 divided by 2. Then you put a bracket on. V you write as Q by A. So you take two brackets, zero point 0.1 divided by, and you do this twice, respectively with all areas and all. Hmm. What is this area? This is 12 centimeters. So 0.12 squared is 0.0144. This is 0.0064, right? We'll take 10 to the power 4 common. So this becomes times 10 to the power 4. Okay, one more thing which I didn't do is square these things out. Control Z. Square is also important. That I didn't do. See, that is the mistake. No problem. So, no. So this is, actually, no, this is incorrect. This should be, this is fine. This should be 0.01. Yeah, this is okay. So now if I take 10 to the power 4 common, and this also out, 10 to the power minus 1 is also out. This only remains 10 to the power 2. Okay. This is becomes 1, this becomes 90. I take 16 common, right? If I take 16 common, this remains as 9. This remains as 4, right? One will become minus 5 by 36. Well, it's incorrect. Some mistake I'm doing. Let me check. Oh, I'm multiplying diameter. I'm not taking pi by 4 also there. Okay. Okay. So that I have to do properly, all those things. I was trying to quickly do it. A is actually not just simply this. A is even more complicated formula. So A will be pi t square by 2. We'll have to do that also. Now, essentially, whatever we'll get is we'll get something like this. That this delta KE will result in how much energy? It will result in this will essentially become uh, essentially this will come as delta. Oh, this will become as dot P P plus delta will come out to be 25.7 kilowatts. This I have to do, this you have to do properly. I didn't do it properly. I was running quickly doing things, but this you have to do quickly. Okay, that is important. Now, if you do this, now that is straightforward. How the overall efficiency will be 25 divided by 35. Okay, this is 35. What is this number? Loosely speaking, this will be 5 by 7, which is how much? 70 point something, right? 74 point something. Okay, this is the overall efficiency. What about the mechanical efficiency? So we will remove the motor efficiency from it. So 74 divided by 0.92 should be our total mechanical efficiency, because we remove the motor from the equation. If I do that and calculate what is 74 divided by 0.92 divided by 0.92, we get 80 point something. So 80% and 74% should be the answer. Let me check. Yeah, that's the answer. Okay, 80 and 74. Let's do one last question, which is there with us. So a soap bubble sitting on a metal ring of a diameter 4 centimeter in flat position and is blown by a kid to produce half spherical surface of 4 centimeter square. How much work is required to accomplish this? Consider the surface tension. See, surface tension, there's a formula for surface tension that the energy associated with surface tension is sigma, which is the surface tension has the units of force per unit length. Okay, this is something that you would need to know, and then the energy associated with it uh, is force per unit length, and now area, which is force per unit uh, area is meter square or length square, gives you force into area. So that is work done. So work done by surface work will have this unit. That is what we need to know for this. Okay. So now we know that there is a change in area. Earlier, this was a metal ring, which is pi d square by 2. So A1 was pi d square by 2 because it is pi r square. Okay. But A2 is half a spherical sphere, which is 2 pi 2 pi r square. Okay. Note that 2 pi r square, which is 2 pi d square by 4. So pi d square by 2, right? So what is the delta A that you're essentially looking at? You're looking at pi d square. Give me a second. Yeah. So as I was saying, pi d square by 4, right? This is the difference you're looking at. And the work, if you want to calculate work done, which is oh, work done is sigma, which is 25 times 10 to the power minus 3 times pi by 4. Diameter is 4 centimeters. So 0.04 square, isn't it? Let me think. Right. So this point I'll remove to get 10 to the power 4 times 4 square. So this 4 and this 4 gets cancelled for me to simply get pi. Pi, and then this 4 times 25 is 100, which cancels with this which cancels with the 10 to the power minus 3 to give you 10 to the power minus 1, and this 10 to the power minus 1 gets cancelled with 10 to the power 4 to give you 10 to the power 3, which is 10 to the power by 3 is 3.14 into 10 to the power uh, 3 joules. Okay. This is minus and minus. Have I missed some 4 centimeters? Sigma is 25 times 10 to the power minus Newton per meter. This should have come. Let me check. So we had this, right? Pi d square by 4. So that is the mistake that I did. Should be 10 to the power minus 4. Okay. That is important times this. Now the same stuff, you do this. So you essentially get pi here. Here you get 100. This is 10 to the power minus 3. So 10 to the power minus 1, which can be agglomerated with 10 to the power minus 5, 4 to get 10 to the power, so 5 times 10 to the power minus 5, which is the last option, 3 to the power pi into 10 to the power minus 5 joules. That is the correct answer. So yeah, that is there. Okay, so now we have kind of exhausted all the questions I had in my repository available to me. If there are any questions, you can ask, or we can close. And I'll wait for some time for you to collect whatever was done and just review it, or you can ask questions. This is something I can. This is just simple algebra, so I don't want to do it. Okay. So this was session 2 for you guys. Starting few things. We start small for few classes and then we'll pick it up. Okay. Let me stop sharing. We'll